everyone. So we're going to talk about relations. Okay. In chapter 1, we talked about the basics of number theory. We defined some sets. Then what we did, we actually defined an operation that connects two sets together and creates a new set. That operation was called the Cartesian product between two sets. It happens that there are more to those definitions. So our objective is talking about relations. So I'm going to just write down this recall for you. Recall, let A and B be two sets. What we can do, we can take these two sets and construct the Cartesian product between them. Remember that the Cartesian product is different from cross product that you learned in calculus. So A, Cartesian product with B is equal to the collection of all ordered pairs like A, comma B or X, comma Y, such that X belongs to A and Y belongs to B. Okay, well, this is just the Cartesian product. For example, in calculus, you learn that if you have the real axis, you have the real axis, x-axis, then we can find the Cartesian product between R, x-axis, and R. What do we define? We define the plane, the collection of all points in the plane. Since there are infinitely many points, instead of just using dots, we say that, hey, we can just shape the whole thing and it creates XY plane or rectangular plane or Cartesian plane for us. So x-axis, y-axis is the same as R. Just for simplicity, we just label these X and Y, but this is actually R and this guy is R. So this is the Cartesian product between R and R gives you all the points in the plane. Cartesian product between two sets. Remember that. We said, okay, now that we have points ordered pairs in the space, in the plane, we can take some collection, sub-collection, subsets of these points and define something that we call a relation. So we said that a relation is a subset of Cartesian products between A and B. Collection of points. Well, sometimes this collection is meaningful. Some other times we cannot follow anything or grasp anything out of that relation. So, for example, if I consider this set, the set of all X and Y, such that X squared plus Y squared is equal to 1, we say that, okay, I know this relation. These relations, I suppose this is in R. X in R, Y in R. Otherwise, you have some dots in XY plane. So, example, the collection of all points ordered pairs like X and Y such that if I square X, if I square Y, their sum is equal to 1. I ask you, hey, identify this relation or graph it. You might say, well, this is not very hard to visualize. Why is that? Because I already know that X and Y, both of them are in R. So I just need to find all points on this unit circle. The collection of all points x comma y such that x squared plus y squared is equal to 1. The graph is going to be this graph representation. Some other times you just have some points in the plane. You might not find anything meaningful relation between them. Also recall that we said if a point like x comma y be in a relation, let us call relation R, belongs to relation R, we write it this way. We can write it as x, R, y. What's the meaning of that? It means that x is related to y in R, or x has a relation with y using R. You might use S, T, any other capital letter can represent a relation between some points either in the space or in Z, Cartesian product with Z, N Cartesian product with N, and many more sets. Another quick example for you. In this example, we're going to define a relation. So we are just writing an example and we're trying to come up with some new relations. Let's think about it this way. Let us define a relation like E as follows. We say that M and N, these are points in the Cartesian product between Z and Z. We say that, well, M is in relation with N. We're going to use letter E if and only if, with the condition that M minus N is even. So what are we trying to do? We're trying to build this relation. How do we represent this relation using set notation? So we're going to define, this is equivalent to saying that, hey, E is equal to the set of all ordered pairs M and N such that M is in Z, N is in Z, and M minus N is even. So these two, they have the exact same meaning, either using set notation to represent this relation, or just mentioning that, hey, M is in relation with N in set E, in relation E, if and only if N minus N is even. Question says, well, list 5 integers that are related to 1. List 5 integers that are related to 1. So we're looking for 5 integers that when we subtract them from 1, the outcome is even. It just says, find just 5 integers. It means that 1 is in relation with n, okay, if and only if 1 minus n is even. Okay, they are in relation with 1, or 1 is in relation with them. We can switch these, it doesn't matter. Later on, you see we have symmetry here, and n minus 1 is even. Okay. We can just randomly select numbers, integers, and check to see if the subtraction is even or not. The very first one, and the m equals to 1. M can be 3, M can be 5, M can be 7, and so on. So you can choose odd numbers. Odd minus 1 gives you an even integer. There you go. You might say, well, these are the things that we saw before. M minus n is even. Can we define something new as a relation? Of course. So let's take a look at this example here. This example says, well, let X be set including A, B, and C. Okay. B and C. It means that the cardinality of this set is equal to 3. It also says define a relation. Define a relation as follows. This relation is S from power set of X to Z. So it's the relation that we're trying to define. This relation defines as follows. A is in a relation with B if and only if A has at least as many elements as B. They have a relation S that takes on values from Px to integer Z. We say that, hey, 2 members from the power set of X are related together, are members of S, if and only if A has at least as many elements as B. Okay, now question says, well, is set including A and B related to set including B and C? Because S, B, is A set including A in relation with empty set? C is set including B and C in relation with set including A, B, C? Very well. Okay. So let me erase this part of the board. It says A is in relation with S, or we define S to be the set of all sets A and B, such that A and B, first of all, they both belongs to power set of X, and A has at least as many elements as B. It means that the cardinality of A must be greater than or equals to cardinality of B. This is the way that we can represent this relation. Okay. So let's take a look at A. The cardinality of this set is 2. The cardinality of this set is 2 as well, since they have the same cardinality. It is true. Okay. The cardinality of set A is 1, and the cardinality of empty set is 0. Of course, since the cardinality of set A is equal to 1, and it is greater than equals to 0, which is the cardinality of empty set, so it is true. But what about this guy? The cardinality of set BC, B comma C, is 2, which is not greater than or equals to the cardinality of set A, B, C, which is 3. So I'm going to define another relation. We talked about divisibility in number theory. So let us use that and define a new relation. So another example for you. Let set A be equal to, well, 2, 3, 4. The cardinality of this set is just 3. And we're going to define another set, 2, 6, 8. B, 2, 6, and 8. And we're going to define the relation R this way. R is a relation which is defined this way. You see that X, so let us take X and Y, belongs to Cartesian product of A and B, and then X is in relation with Y if and only if X divides Y. So in another word, we can write down this relation this way. R is the collection of ordered pairs X and Y such that X belongs to A, Y belongs to B, and X divides Y. Question says, well, describe R inverse. And then question says, graph this relation. Okay. They have a relation. We want to know what is the inverse of that relation. First of all, recall that from algebra. If we have a collection of points, X and Y's, if R is defined as the collection of AB, CD, EF, the inverse of that relation is by switching X and Y's. So it's going to be equal to B and A, D and C, F and E. That's how we define the inverse of a relation by switching X and Y's. AB, this is your X, B is your Y. Now B is your X, Y is A, and you continue this process. You're flipping X and Y's. Okay, so first you need to know what is R. What are the elements in R? Okay, let us describe R first. We know that we have to have all the elements in the Cartesian product between A and B. So you get 9 ordered pairs. R is a subset of Cartesian product between A and B. So we can list them all. Here you have 2, 2, 2, 6, 2, 8. Then you have 3, 2, 3, 6, 3, 8. Then you have 4, 2, 4, 6, and 4, 8. Out of these points, we're looking for the values, the points such that X divides Y. The first coordinate divides the second coordinate. Is the first one acceptable? Yes, of course. 2 divides 2. So 2 and 2 is the very first element in relation R. 2 divides 6, of course. So the next point is 2 and 6. 2 divides 8, of course. 2 and 8. 3 and 2, no. 3 and 6, yes, of course. 3 and 8, not a chance. 4 and 2, of course not. 4 doesn't divide 2. 2 divides 4, but 4 doesn't divide 2. 4 and 6, no. 4 and 8, of course. So this relation has these points. We can easily describe the inverse of this relation by switching X and Y's. For the first point, it doesn't matter. You have 2 and 2. For the second point, you get 6 and 2. For the third point, 8 and 2. Then you have 6 and 3. Then we have 8 and 4. And that's it. So this is our inverse R. Okay. So note that this is my relation, collection of points. X divides Y. The second part says, hey, graph this relation, visualize this relation. Actually, we call this directed graph. So the official name for it is directed graph. Well, how does it work? Okay. We're going to list all elements in A and B. 2, 3, 4, 6, 8. This relation is a subset of Cartesian products. Okay, so 2 is connected to 2. 2 is connected to 2. It means that we're going to use a loop representing this relation. 2 divides 2. 2 is related to 6, but note that 6 is not related to 2. 2 is related to 6, so we're going to connect 2 to 6 by an arrow coming from 2 and going to 6. 2 and 8. Well, okay, 2 is related to 8, an arrow coming from 2 and ending at 8. 3 is connected to 6. Okay, an arrow coming from 3 and stops at 6. What else we have? 4 and 8. 4 is connected to 8. An arrow coming from 4 and lands in 8. This is called the directed graph. So let's see. That's it. The question asks about describe the inverse relation and graph the relation using directed graph. Very well. We're going to go over more definitions. We have special types of relations. We have reflexive relation, we have symmetric relation, and we also have transitive relations. So let's write down this definition. Then we're going to go over some examples. Types of relations. Reflexive relation. So first of all, let R be a relation on set A. What's the meaning of that? It means that R is subset of Cartesian product between A and itself. So when we say R is a relation on A, it means that R is a subset of Cartesian product between A and A. We say that this relation is reflexive if it follows the following property. R is reflexive if and only if you take any random element. If you take any random element in A, that element is related to itself through R. If and only if for any x in A, x is in relation to itself over R, or x and x belongs to R. We say that R is symmetric. Symmetric. R is symmetric if and only if for any x and y in A. For any x and y in A. If x is in relation with y, then you can conclude that y is also in relation with x. If x is in relation with y, then you can conclude that y is in relation with x. Or if x and y is a member of R, you can conclude y and x is a member of R. And finally, we have transitive. Transitive relation. R is transitive if and only if for any x, y, and z in A, if X is in relation with Y and Y is in relation with Z, then you can conclude that X is in relation with Z. Okay. Reflexive, symmetric, transitive. Guys, note that when you're analyzing these symmetric and transitive, you must have this condition. If you see a relation between X and Y, you can move on. If you see a relation between X and Y, and you can see a relation between Y and Z, then you can move on to next step. If you don't see any relation between those values, it doesn't mean that the relation is not transitive. Okay? So let's take a look at this example. Ask you to solve this example. Analyze the following. Which one is reflexive, symmetric, transitive? The first one says, first let's define set A. Set A is the collection of 0, 1, 2, and 3. Okay. Well, R, relation R, is defined as the collection of 0, 0. What else we have? 0, 1. What else we have? 0, 3. What else we have? 1 and 0. What else we have? 1 and 1. Okay. 2 and 2. 3 and 0. 3 and 3. This is your first relation. The second relation is S, which is defined as the collection of 0, 0. These points, 0, 2, well, 0, 3, okay, and 2 and 3. Now check the last relation T, which includes 2 points, 0, 1, also 2 and 3. Okay, so being reflexive, if and only if for any X in A, X is in relation with itself, or the point X and X belongs to the relation. So as you can see here, your set A has 0, 1, 2, 3. As long as you have 0, 0, 1, 1, 2, 2, 3, 3, then you're good with reflexive relation. Okay, I see 0, 0, I see 1, 1, I see 2, 2, I see 3, 3, so it is reflexive. Well, is it transitive? What's the meaning of that? It means that if X is in relation with Y, then you can conclude that Y is also in relation with X. So what do we have here? I have 0, 1. Do I have 1, 0? Of course. I have 0 and 3. Do I have 3 and 0? Yes. Do I have anything else to check? No. So it is symmetric. Very well. So let us consider transitive. If X is in relation with Y and Y is in relation with Z, I should be able to conclude that X is in relation with Z. Okay, let's see. What do we have here? I have 0, 0, 0 and 1. I have 0, 1. 0, 0, 0, 3. I have 0, 3. What else do I have here? I don't have any 0 to be worried about. 0 and 1, 1 and 0, 0 and 0 is here. 0 and 1, 1 and 1, I get 0 and 1, which is just right here. What about 0, 3? 0 and 3, 3 and 0. Okay, do I have 0 and 0? Yes. 0 and 3, 3 and 3. I get 0 and 3, which is just right here. Well, let's take a look at this. 1 and 0. Okay. 1 and 0. I already checked 0 and 0. I have 1 and 0 there. I have 1 and 1 there. Okay. I have 1 and 1. Then I have 2 and 2. Then I have 3 and 0. 3 and 3. Okay. What's missing here? Can we conclude that this is a transitive relation? Why it is transitive, why it's not transitive. So take a look at this. You have 1 and 0. You have 0 and 3. Take a look at this guy. So it says 1 and 0. 1 is connected to 0. 0 is connected to 3. Do you have 1 and 3 in the collection? You don't have 1 and 3 in this collection. 1 and 3 is missing, so it's not transitive. Transitive? No. So one more time. Every element is connected to itself in R. 0 and 0, 1 and 1, 2 and 2, 3 and 3. So here we have the reflexive property for this relation. For being symmetric, we need to check to see if X and Y is in this relation, then Y and X is also in this relation. So let's check each of them one by one. 0 is connected to 1, 1 is connected to 0. 0 is connected to 3, 3 is also connected to 0. So these two. What else? That's it. So we only have 2 sets of points to check. So it is symmetric. Now, for being transitive, if X is in relation with Y, Y is in relation with Z, we need to be able to connect X to Z. But we can find 2 points. What are those 2 points? One of them is 1 and 0. The other one is 0 and 3. 1 is connected to 0. 0 is connected to 3. But 1 and 3, 1 is not connected to 3 in this relation. That's why it's not transitive. Very well. So let us take a look at this relation. Is it reflexive? So far I have 0 and 0. I don't have 1, 1. I don't have 2, 2. I don't have 3, 3. Take a look at the definition. It says for any X in A, you need to see X and X in that relation. So it's not reflexive. Is it symmetric? Well, okay, let's start checking. 0 is connected to 2, but I don't have 2 and 0. Not 2 and 0. So it's not symmetric. So take a look at the definition. It says if X is related to Y, then you need to be able to conclude that Y is connected to X. I have X connected to Y, but I don't have Y connected to X. So it's not symmetric. Now, transitive. Is it transitive? Take a look at this. You need to have two points to conclude that you have X and Z related together. As long as you have 2 points, you're good for the conclusion. If you don't have 2 points, you just don't say it's not transitive. So take a look at this. You have 0 and 2, 2 and 3. Okay. 0 is connected to 2. 2 is connected to 3. Do I have 0 connected to 3? Yes, of course. 0 connected to 3. Well, do I have anything else to check? I have 0, 0, 0, 2. I already have 0 and 2. What else? That's it. 0, 0, 0, 3. I also have 0 and 3. So it is transitive. Awesome. So is this guy reflexive? We don't even have 0, 0 there. So nope, it's not reflexive. Is this guy symmetric? Well, I have 0, 1, but I don't have 1 and 0. So 0 is connected to 1, but 1 is not connected to 0. So symmetric? Nope. What about reflexive? Okay. 0 is connected to 1. Do I have 1 connected to something else? Guys, note that in the definition, if x is in relation with y, and you need to have your second point. Do you have your second point? 0 is connected to 1. You don't have anything about 1 connected to something else. So we cannot decide about this one. What about 2 and 3? 2 is connected to 3. 3 is connected to, I don't have the second point to move forward and check this relation. So it is transitive. Very well. So give us more examples. Example. Suppose we define a relation this way. We say that, well, let R be defined on Cartesian product between the real line by itself. Remember that this guy is just a plane. So here you're dealing with a plane. So you are taking a collection of points in the plane. But how do we define this relation? We define it this way. For all x and y in R real numbers, x is in relation with y if and only if x is less than y. Question says, hey, is this reflexive? Is this symmetric? And C, is this transitive? Which case is this? Here we go. So is this reflexive? Remember the definition of being reflexive. Take 1, for example. Can we say that 1 is less than 1? Is this true? Of course not. So not reflexive. Is this symmetric? Take 1 and 2. 1 is less than 2, but 2 is not less than 1. It's not symmetric. Is it transitive? Well, if 1 is less than 2 and 2 is less than 3, then we can conclude that 1 is less than 3. So the only property that this relation has is being transitive. We're going to define a new relation on Z. So define T on Z. T be a relation on Z. And we define it this way. We say that for all integers, M and N, M is in relation with N if and only if 3 divides the difference between M and N. What's the meaning of that? It means that M minus N is equal to 3K, K is an integer, or M is N plus 3K. That's the meaning of that. Okay, the question says, well, do you have a reflexive relation? Do you have a symmetric relation? Do you have a transitive relation? And another question for you is, can you generalize this into divisibility by like L? M is in relation with N if and only if an integer like L divides M minus N. Is it transitive? Is it reflexive? Is it symmetric? Which one is that? So another question for you. Can we generalize this relation? Well, is it reflexive? So it means that M must be connected with itself. M is in relation with M. It means that 3 divides M minus M. Does 3 divide 0? Of course. 0 can be written as 3 times 0. So it is reflexive. Is it symmetric? It means that if M is in relation with N, can we conclude that N is in relation with M? Or in another word, if 3 divides M minus N, can we conclude that 3 divides N minus M? Okay, we know the definition of divisibility. We know that there exists an integer like K, that M minus N is equal to 3K. Okay, now multiply both sides by negative sign. You get N minus M equals to negative 3K. But negative K can be called like L. So N minus M is equal to 3L. What's the meaning of that? It means that 3 divides N minus M. So it is symmetric. Well, is it transitive? What's the meaning of that? It means that if 3 divides M minus N and 3 divides N minus an integer, let us call it, I don't know, which one you prefer. N minus, let's call it Z, or S is there. So 3 divides M minus N, 3 divides N minus N. Can we conclude that 3 divides M minus S? Can we do that? Well, let us follow the definition. 3 divides M minus N. It means that there is an integer like k sub 1, that m minus n is 3k sub 1. 3 divides n minus s, it means that n minus s is equal to 3k sub 2. Well, now I just say add these. Add them. If you add these, so you can cancel out negative n and n, what's left? You have m minus s, which is equal to 3 times k1 plus k2. This guy can be called L. 3 divides m minus s. So here we have 3 divides m minus s. So it is transitive as well. When a relation is reflexive, symmetric, and transitive, we call it an equivalence relation. So, equivalence relation. It is reflexive, it is symmetric, and it is transitive. So in general, divisibility is an equivalence relation. So the answer is yes.
Execute.